Assalamualaikum to Dr. Aizuddin. My name is G6-E5-SETG3751-Thermo-Materials-Lab and I'm from Group 6. So in this video, we are going to present Experiment 5, which is bending moment. My group consists of Sri, Ling, Devaraj, G6-E5-Fadlila, and Zafran bin Zainal. So for abstract, bending moment is a crucial factor if you want to design any structural component. This is because bending moment can help to calculate where and how much bending might occur to a structural element when forces are applied. So in this experiment, we are going to measure the bending moment of the material used by using the experimental beam, load hangers, load, and also spring balance. So in order to determine the bending moment, we can determine from the reading of spring balance obtained when we use different loads later. So at the end of this experiment, we can compare the experimental and theoretical values of bending moments. The values of experimental and theoretical obtained later might differ due to the parallax error that will be discussed at the discussion part. Then we can also analyze the effect of loads to the bending moment in the discussion part. Now I will proceed with introduction. So bending moment experiment is conducted to measure the bending moment of the material. So bending moment generally can be defined as traction induced in a structural element when an external force or moment is applied to the element which it will cause the element to bend. The common element which can be subjected to bending moment is beam. So that's why in this experiment, we are using experimental beam that is divided into two parts, which is part A and part B, where part A is smaller than part B, and then it will be connected by a joint to form a frictionless hinge. So, and then the load will be induced to the beam using load hangers, where we can take the reading of the spring balance. This is because when we place the load at the beam will start to bend, and then the spring balance will align the beam. So that's why we need to record the reading of the spring balance to calculate the bending moment later. So in order for us to measure the bending moment, we need to depend to the value of the spring balance reading. The steps in this experiment will be repeated by using different weight of loads so that we can analyze the different values given by the spring balance later. So at the end of this experiment, we can compare the experimental bending moment with the theoretical bending moment, and also we can see the effect of loads towards the bending moment values.
Hi everyone, my name is Zafran. I'm gonna take the theory part. Okay, for this theory, the example shows a beam which is simply supported by both ends. Simply supported means that each end of the beam can rotate, therefore each end support has no bending moment. The ends can only react to the shear load. Other beams can have both end fixed, therefore each end support has both bending moment and shear reaction loads. Beams can also have one end fixed and one end simply supported. The simplest type of beam is the cantilever, which is fixed at one end and is free at the other end, neither simple or fixed. In reality, beam supports are usually neither absolutely fixed nor absolutely rotating freely. The bending moment at any point along the beam is equal to the area under the shear force diagram up to the point. For a simply supported beam, the bending moment at the ends will always be equal to 0. To calculate the bending moment, the beam must be broken up into two sections. For the first one from x equal to 0 to x equal to L over 2, and the other another one is the other from x equal to L over 2 to x equal to L. Thank you, and I'll pass to the next person.
Hi, I'm here to explain the apparatus and the methodology. For apparatus, there are three, which are experimental beam, load, and load hanger, which we can see in figure below. For methodology, there are two parts, part 1 and part 2. For part 1, the beam was set up so that the bearing pin part B is 300 mm from the left hand support and 600 mm to the right hand support. And then one load hanger is placed on the middle of the smaller part A of the beam and one of the larger part B, and the third one at the joint just over the bearing pin. Then two parts of the beams align using the adjustment on the spring balance and record the initial reading using table 1. Then 10 Newton, which is 1 kg weight on part B's hang, realign and they realign the beam and the new reading is recorded on the spring balance using table 1. The difference between the two readings and the effect is the effect of applying the 10 Newton, which is 1 kg weight on the beam. The distance is recorded using table 1 from this weight to the right hand support. Then the procedure is repeated by using the hanger over the bearing pin and then the hanger on part A. Finally, the whole process is repeating by using a 20 Newton, which is 2 kg load. For part 2, 3 load hangers is placed at desired, align the beam and record the initial reading of the spring balance using table 2. Then the weight is put on all the 3 hangers, realign the beam and record the new balance reading using table 2. The experiment is repeated in part 2 with a different position and loading. Record the new balance reading using table 3. That's all from me. I pass it to the next person.
Hello, my name is Sri, son of Nagindra Rao, and I'm going to explain about the results of this experiment. So for this experiment, we have given that we have been tested from part 1, part 2 and part 3. So each have 3 different values and 3 different results, and we have 3 types of different graphs. So for the first part, so we have a load of 0, 10 and 20. Then we have given results, we have got the results about balance reading and the net force for load at P1, P2 and P3. So for the 0 Newton, we have given 20 over 0, 20 over 0 and 20 over 0, which is same because there is no load. So for the 10 Newton, we have got 24, 32 and 26 at P1, P2 and P3. And for 20 Newton, we have P1 28, P2 44 and P3 32. So for this, we have to find the bending moment, which can be found using the calculations and also the theoretical value. So for 10 Newton, we have got 600 the bending moment and the theoretical value is 667 at P1. For P2 at 10 Newton, we got 1800 as bending moment and theoretical value is 2001, and 900 bending moment at P3 and theoretical value 999.9. For 20 Newton, we have got bending moment at P1, which is 1200 Newton millimeter, and theoretical value is 1333 Newton millimeter. For P2 at 20 Newton, we have got 3600 as bending moment and the theoretical value is 3999 Newton millimeter. And at P3 at 20 Newton, we have got 1800 Newton millimeter as the bending moment and the theoretical value is 2000 Newton millimeter. So now these are the calculations steps that we have used. For example, now we are taking at P1 when the weight is 10 Newton, the bending moment at C, which is moment at C is equal to net force times by 150 millimeter, which is the distance from the point. So now we can do 24 minus 20, which is the balance reading is 24. So minus with initial balance reading, which is 20 Newton, and times by 150 millimeter, we have got 600 Newton millimeter as the moment of the experiment. So to find the theoretical value, we have to know the RA and RB. So we know moment at B is equal to 0. So then we can use the formula that we have learned to find the RA. Once we find the RA, then we can find the moment at C theoretical. So by using the formulas and the FBD, we can find that moment at C theoretical, which is 667 Newton millimeter. Same goes for weight 10 Newton at P2 and at P3 too. So next we're going to see the graphs that we have obtained from the experiment, from the results. So these are the bending moment graphs, which is for bending moment at C when the weight is 10 Newton and bending moment at C when the weight is 20 Newton. Next we're going to see the table to data for bending moment at C for the load configuration for part 2. So in part 2 we have two types of situation where at point 2 5 Newton load is added, and the second situation is point 1 and point 3 is added 10 Newton and point 2 is added 5 Newton load. So the balance reading was 18 Newton when there is no load added, and when we add 5 Newton at point 2 we got 25 Newton, and the third situation we have got 36 Newton. So from there we can find out our bending moment using the calculations and theoretical value too. So for load at 5 Newton at P2 we can find the bending moment at C, which is equal to net force times 150 mm. So we know the initial is 18 Newton, so we can minus the balance reading 25 Newton minus 18 Newton and times by 150, which is 1050 Newton millimeter. Then we can find the value of RA and RB from the FBD, where we know that moment at A is equal to 0. As the summation of moment at A equal to 0, then we can find the RB, which is 1.67 Newton, and then we know summation of Fy is equal to 0, then we can find the Ra, which is 3.33. Then we can find the moment at C theoretical by Ra times by 300 mm, which is the distance from the point C. So then we can get the bending moment of the theoretical value, which is 999 Newton millimeter. Same goes for the second step. We got moment at C for the second situation 2700 Newton millimeter, and MC theoretical at 2668 Newton millimeter. Next we're going to see the graphs for the second part, which is the bending moment at C when P2 is added with 5 Newton, and bending moment at C when the point 1 and point 2 is added with 10 Newton and point 2 is equal to 5 Newton. For the third part, we have given again same as the part 2, where there has been 3 situations, where the first one there is no weight is added, and the second where the point 1 is added with 5 Newton and point 3 is added with 12 Newton, and the third situation is point 1 is added with 5 Newton, point 2 is added with 10 Newton and point 3 is added with 2 Newton. So the balance reading was for the first was 20 Newton, which will be the initial reading. Then for the second situation it will be 30 Newton, and for the third situation is 36 Newton. So we have to find the bending moment and bending moment theoretical value. So for this we can find using the calculation, where for the load equal to 5 Newton at P1 and load equal to 12 Newton at P3, where the moment at C is equal to net force times 150 mm. So we know that the balance reading was 30 Newton and the initial reading was 20. So we can times with 150, then we can get the moment at C, which is 1500 Newton millimeter. So for the next, we know that moment at A equal to 0, and find the RB, which is equal to 7.22 Newton. Then we also know the summation of Fy is equal to 0, so we can find Ra from that, which is 9.78 Newton. Then we can use the formula MC, the moment at C theoretical equal to Ra times 300 and minus P1 weight at P1 times 200, where we obtain about 1931 Newton millimeter as the moment theoretical. Same goes for the second situation, which is for load equal to 5 Newton at P1 and load equal to 10 Newton at P2 and load equal to 2 Newton at P3, where we got the moment and bending moment at C, which is 2400 Newton millimeter, and bending moment at theoretical is equal to 2600 Newton millimeter. So now we're going to see the graphs where the bending moment at C when P1 equal to 5 and P3 equal to 12 Newton, and bending moment at C P1 is equal to 5 Newton, P2 equal to 10 Newton, P3 equal to 2 Newton. So that's all from me. Thank you.
Good day, Dr. Aizuddin and also fellow friend. My name is Tan Pek Ling. I will be explaining about this discussion. So in this discussion, the result that we gain in part 1 actually follow the theory about this bending moment, since the theoretical value of bending moment is stable when the load is stable. And experimental value also double as well when the load increases. From the result that we get, right, the bending moment were different when the same load was placed at a different position. The nearer distance between the load and balance, the higher the value of the moment that we get, the bending moment that we get. So according to the result in part 2, the value of bending moment increased when net force increased. Therefore, we can conclude that the bending moment was affected by the position of the load as well as the net force of the load. So by answering to this question, when the load was double in part 1 of the experiment, did the bending moment double? For sure, it is a yes according to the theory. This can be explained by the formula of the bending moment, which is the bending moment is actually the product of net force caused by the load with the length of span of the spring balance. So the length of the span of the spring balance actually is the same for everyone. So is 150 millimeter. So when we use the formula to get the answer, the bending moment is directly proportional to the net force caused by the load. So when the load is double, net force will be double as well. Hence, the bending moment will be double too if experimental value did not follow this theory. So it's probably due to some unexpected issue or error occurring during the experiment if let's say the value didn't follow the theory that I mentioned just now. So here is actually the result that we get lah. Yeah. As you can see here, the bending moment 600 is the experimental, and then this is the theoretical bending moment. So discussion 2. Compare the average figure for each of the experiment by using the bending moments value obtained from the experimental and also theoretical. Use either a ratio or percentage error. So the formula is as follows. Percentage error equal to theory minus experimental over theory times with 100%. And the number is actually modulus, absolute value. And then the average error is equal to the total percentage error over the number of percentage error. So here is the result, the percentage error that we get for the part 1 data. So the average error for the part 1 is 10.01%. And in part 2 is still the same. The calculation method is the same. So we use this theoretical value minus the experimental value of the bending moment and divide by the theoretical value. Then times with 100, then we will get 5.11% for the P2 equals to 5 Newton. And for P1 equals to P3 equals to 10 Newton and P2 equals to 5, the experimental bending moment is 2,700 and theoretical is 2,668. So the percentage error is 1.20%. And total the average error we get is 3.15%. And for part 2b, the load for the load of like P1 equals to 5 Newton, P3 equals to 12 Newton, and P1 equals to 5, P2 equals to 10, and P3 equals to 2 Newton. The bending moment for the experimental for P1 equals to 5 and P3 equals to 12 is 1,500, and theoretical is 1,934. And the percentage error will be higher here, like much higher, which is 22.44%. And for the P1 equals to 5 Newton, P2 equals to 10 Newton, and P3 equals to 2 Newton, the experimental bending moment is 2,400 and theoretical is 2,600. And the percentage error here is 7.69%. So average error here will be 15.07%, which is much higher compared to part 2A and also part 1. So based on the table 4.01, we can observe that the percentage error for part 1 and part 2B are quite higher compared with the part 2A. The average error for part 1 is 10.01%, while part 2A is 3.15% and 15.07%. stand for the part 2b. This is because of the error is actually occurring during the experiment. So here is actually some error that may happen during the experiment. First is the scale of the spring balance is actually not precise enough for the accurate measurement. So this is actually because of sometimes the apparatus is old and which has not been maintained or maybe renewed. So it might lead to this inaccuracy of the reading that we get. And the next one is actually the parallax error that will happen when we are taking the reading of the spring balance, as well as checking the position of the air bubble. This is because sometimes our eye level is actually not perpendicular to the spring balance, and the next one is the movement of the hanger that might affect the reading as well when the hanger is not parallel to the spring balance. So to prevent all these errors to happen, there are several precautions that we can take. So first one is actually we can use a more precise spring balance and also repeat the experiment to get the average reading, to get the average result, so that we can solve the problem caused by the apparatus problem. And the next one is to prevent the parallax error. So to prevent parallax error, we should always make sure that our eyes, okay, or the observer eyes should be perpendicular to the spring balance scale when we are taking the readings. And lastly is actually always check whether the hanger is in the correct position before we take the readings. So I think that's all from me. I will pass it to my friend, Safran.
For the conclusion, this experiment were to study the effect of different forces on the bending moment in the beam, and the results show that there is a linear relationship between bending moment and applied load. Experimental and theoretical bending moment shows perfect linear relationship with applied load, with very little difference in the values of bending moment. Thank you.